Mean group on the left here. What's the geometry of this? Tetrahedral. That's the electron pair geometry. What's the molecular geometry of this? Trigonal pyramidal. Good. So this is trigonal pyramidal. This is tetrahedral. And then the second carbon, both are the same. This carbon is tetrahedral. This carbon is planar. Yeah, trigonal planar. This is all flat in the plane. This oxygen is tetrahedral electron pair geometry. But normally when people ask about the shape, they're asking about the molecular geometry. Not the electron pair geometry is an important intermediate step. We got to figure out the electron pair geometry or the set geometry or the electron group geometry before we can figure out the molecular geometry. But ultimately, we want is the molecular geometry. At the end is going to be bit. So that's it. All right, so this is the drawing. We can figure out the angles here, 109, 109, 120, 109 kind of thing. Those would be the ideal angles. So that's what we see. So any questions on this? The shape of propanoic acid? All right, we're going to continue where we left off. We were talking about gases. Where did we leave off? Did we do this calculation here with helium? Yeah?
No.
No. This one?
Yeah.
All right. All right, so we come up with the ideal gas law. Basically, in this chapter, the two main equations that you need to remember. This one, PV equals nRT. When we have PV equals nRT, we know what R is. What is R? 0.08206 units, liters, atmosphere per mole Kelvin. And so basically the main type of calculation that we're going to do with this is solve for a single variable. If we're given 3 out of the 4 variables, then this is a constant. So if we're given 3 out of the 4, then we can solve for the 4. And so as far as calculations go, the primary calculation is just to solve for the variable, one of the variables, pressure, volume, moles, or temperature. And that's what we did in this problem. We solved for, well, actually, this is solving for R. Yeah, solving for a variable. This is the slide here. So in this slide, the first half of this slide is just a common calculation for the ideal gas law, or the ideal gas equation, to solve for a single variable. The second half is a special application of this. And so there are special applications of the ideal gas law. All right, the first special application is molar mass. It's a little bit different, but I'm going to deviate from that slide a little bit. And so if we're looking at MM, which is equal to the molar mass of a gas, or the molar mass of anything, is just equal to the grams per mole. How many grams are there in a mole? That's what the molar mass is. And in terms of a gas, the grams will be the mass, and the moles is just given by N. So the mass over moles, grams per mole. For a gas, we can calculate the number of moles. The number of moles is equal to PV over RT. Just simplify that equation there. And then we'll just substitute that in here. If we substitute it, then the molar mass is equal to the mass divided by PV over RT. And then we'll just invert and multiply. So we get the mass times RT divided by PV. And so this is a relationship, a special application of the ideal gas law. We can use ideal gas law to calculate the molar mass. Actually, we really didn't have to do two equations for this. One, we could have just used the ideal gas law to solve for n and then plug in n here, given the mass. But there's one thing that we might note here, and that is we try to relate things to other stuff. So if I look at this, mass over volume, you know what mass over volume is usually called? Mass over volume is called density. And so we'll just say, but the mass over volume is equal to the density. And so what we can do here is just go this and then substitute density for that. So this is going to equal the density times RT over P. And so we can relate the molar mass, you know, to the temperature, pressure, and volume, or we can relate it to the density. Temperature and pressure. Okay. So in other words, we can calculate the molar mass of the gas. All right, the second thing is we can calculate the density. D. The density, we can rearrange this equation, which we just generated, or we can just derive a new equation for that. Density is equal to the mass over volume. But from the ideal gas law, the volume is equal to nRT over P. And then we'll substitute it. If we substitute it, we'll get density is equal to mass divided by nRT over P. And then we'll invert and multiply. So we get the mass times P divided by nRT. We've seen this before. Mass over moles, grams per mole. Where did we see that? Grams per mole. Yeah, this is a molar mass. And so what we'll do here is we'll just substitute that in here. The density is equal to the molar mass times P divided by RT. So we can calculate the density of any gas as long as we know what it is. We know what the molar mass is. So for example, if I wanted the density of helium at 1 atmosphere pressure of, let's say, minus 10 degrees C, I can calculate it. In fact, I can just change the temperature and pressure and just calculate. I don't have to actually measure the density of the gas. So this allows for calculation. Density. And so let's do a calculation here. The density of a gas. Oh, did we already do this calculation here? No. Okay, this is a calculation of just the standard. What is the pressure? Actually, I forgot to do this calculation. Let me do one more here before, and one more special application. The last special application is the molar volume, MV. The molar volume. The molar volume of the gas, MV, is equal to the liters per mole. In other words, it's going to be volume over N. And so what we're going to do is we're going to take PV equals nRT and just rearrange it, or we'll do substitutions, either. If we take the pressure divided by both sides and N divided by both sides, then we'll get we get V over N is equal to RT over P, the molar volume here. And so the molar volume is equal to RT over P. In other words, we can calculate, how many liters a mole of gas occupies at any temperature and pressure using this equation. And so these are some special applications for the ideal gas law. And so let's take a look at some calculations here. First calculation is, what is the pressure in a helium-filled 0.77 liter balloon if it contains 1.0 grams of gas at 22 degrees C. All right, so they want to know what the pressure is. Well, we need the volume. What is the volume? The volume is 0.77 liters. We need N, the number of moles. The number of moles, well, it's 1.0 grams of helium gas. So we need to go from grams of helium gas to moles of helium gas by using the molar mass. So mole of helium gas weighs 4.002 grams. Moles of helium gas. Moles of helium gas. Let's go ahead and do that calculation. 1 divided by 4.002. 0.2498. 0.2498. I'm going to carry some extra digits and just avoid round off. There, 1.0987. Okay, and then the temperature. The temperature has to be in Kelvin, so it's going to be 22 degrees C, which is equal to how many Kelvin? It's going to be 295 Kelvin if we add 273 to that. And so if I'm given 3 out of the 4, then I just use some algebra to calculate the fourth, which is going to be the pressure. So this is just a standard ideal gas law calculation. P is equal to nRT over V. And so N, just calculated that, it's 0.2498 moles. R is 0.08206 liters times atmosphere per mole Kelvin. T is 295 Kelvin. And then finally, V, 0.77 liters. So we just got to make sure the units work out. Let's take a look at the moles cancel, Kelvin cancels, liters cancel. So that gives me atmospheres, which is what I want. Atmospheres of pressure. So let's take a look at the. So I'm just going to use all the digits of my calculator to clear it. And so times 0.08206 times 295 divided by 0.77. 7.85 liters. Or not liters, atmospheres. 7.85 atmospheres. I'm only allowed 2 sig figs because of that. So it's going to be 7.9 atmospheres. Let's see what they got here. Yeah, 7.9 atmospheres. They put it all in one equation here. You know, they use this special equation here, you know, but we really didn't need to use that special equation for this particular problem. This is just a standard problem. You know, in other words, they said, well, in order to figure out the number of moles, we take the mass and divide it by the molar mass, but it's not necessary. So I just use the standard PV equals nRT. I don't want to memorize too many equations, different equations. So these are the special applications we looked at, so I'm going to skip that and move on to the problem here. All right, so this is an example here. Let's try this next active example. What is the density of helium at 22 degrees C at 744 torr? Well, this one I'm going to have to use this special equation. You know, the special equation is for the gases here. So what is the density of helium? So we got helium gas. It's going to be at 22 degrees C. 22 degrees C, that's going to be 295 Kelvin and 744 torr. For temperatures, we always have to convert the temperatures into Kelvin, but pressures we might be able to leave as is, or we might have to convert. Okay, now the density equation, we either derive that or we remember it, memorize it. The density is equal to the molar mass times P over RT. Is that correct?
Yeah.
But we can tell if it's incorrect. The way we can tell if it's incorrect is if we get the wrong units. You know, if we look at the units and the units don't work out, the density's got to be in units of grams per volume. The volume for, you know, for gases, typical densities are grams per milliliter, but gases are mostly empty space and they aren't very dense. So we usually use for gases grams per liter. All right, what's the molar mass of helium? Molar mass of helium is 4.002 grams per mole. That's off the periodic table. What's the pressure for this? The pressure is 744 torr, so I'll just leave the pressure in there. R is 0.08206 liters atmosphere per mole Kelvin. And then the temperature is going to be 295 Kelvin here. So we're going to check the units here to see, you know, the units work out or not. And so the units here are going to be, well, moles cancel, Kelvin cancels, atmospheres and torrs don't cancel, but they're related. You know, they're both pressure units. And so what I'm going to do is I'm going to convert the torr into atmospheres. Do you know the conversion factor for torr into atmospheres? Turns out 1 atmosphere is equivalent to 760 torr. So then the torr cancels, and then the atmospheres cancel. And that leaves us with units of grams per liter. See, if we use the wrong equation, we wouldn't have gotten the correct units here. The wrong equation is going to give you with the wrong units. And so even if you have it memorized and you get it wrong by accident, you usually figure it out based on dimensional analysis. And so let's go ahead and do the calculation here. It's going to be 4.002 times 744 divided by 760 divided by 0.08206 divided by 295. 0.1618. 0.161. I'm allowed, looks like 3 sig figs, so I'll just take one extra. 0.1618 grams per liter. So a liter of helium only weighs 0.1618 grams, or 161.8 milligrams. We can round that to 3 sig figs, which would be 0.162 if we wanted to. Which the book did. The book rounded 0.162. When you look at the book's solution, they use a different value of R. The R value that they use is 62.4. We use 0.08206. What's the difference between the book's R and our R value? The difference between the book's R and our R value are the units. We did units of liters, atmosphere per mole Kelvin. They're doing liters torr per mole Kelvin, but you know, do you want to memorize multiple R values depending on what units you use? No. The easiest thing to do is just memorize one and then convert. So what we did was we memorized this one and then we just converted torr into atmospheres and it works. Rather than memorizing a different R value for torr, which is not a good idea. Okay, this is a molar volume. So let's do some molar volume calculations. This is a molar volume calculation at something called STP. So molar volume would be a special application of this. Density is probably one of the most common calculations because we can get the density of gas at any temperature and pressure. You know, usually the higher the pressures and the lower the temperatures, the greater the density of the gas. Molar volume also changes with temperature and pressure. And so the next example we're going to do is we're going to do the molar volume at STP. Well, STP stands for standard temperature and pressure. Standard temperature and pressure. Standard temperature and pressure, the temperature is going to be 0 degrees C, that's standard temperature, and the pressure is going to be 1 bar. And so STP is 0 degrees C or 273 Kelvin and 1 bar pressure, as shown up here. And so we have to think back at the molar volume. So you're either going to memorize this equation or derive it. The molar volume is equal to, what is it equal to? RT over P. RT over P. Well, let's see if I got it right. You know, the units will tell me if I got it right or wrong. And then I'll have to play around. If I got it wrong, then there are two things I can do. I can go back and derive it, or I can just play around with it to get the right units. What are the right units? Well, molar volume should be liters per mole. And so I'm going to go 0.08206 liters atmosphere per mole Kelvin. The temperature is going to be 273 Kelvin. The pressure is going to be 1 bar. Now there's an R value that has 1 bar in there, but should we memorize that R value? No. What we're going to do is we're just going to make sure the units work out. If I look at this, the Kelvin cancels, but the atmospheres and bar don't cancel. The atmospheres and bar are related. Do you know the relationship? In 1 atmosphere, how many bar are there? In 1 atmosphere, there are, this number you don't have to memorize, there are 1.01325 bar. And so the bar cancels, the atmospheres cancel, and we're left with liters per mole. So I got the equation right. I want liters per mole, I got liters per mole. So we'll go 0.08206 times 273 divided by, or no, times 1.01 times 1.01325. This number you don't have to memorize. This conversion you're going to be given. Conversion from bar to atmosphere. And I get 22.69 liters per mole. So we can round that to 22.7 liters per mole. So what does that mean? Well, what that means is that 1 mole of gas occupies about 23 liters. 1 mole of gas. But that's at 0 degrees C. Is 0 degrees C a very common temperature that you work at? No. It's not. What's a more common temperature that people work at? 25 degrees C. So let's redo this. You know, when I was a student, I had to memorize this number. I had to memorize the molar volume at STP. And I was taking, yeah, did I tell you? I had to memorize it, so I memorized it. And ever since then, do you know how many times I've used that number? 0. And but the problem is I have it memorized. I cannot unforget that number. I mean, it's stuck. It's a waste of memory, but this one is a better number to memorize. Molar volume at 25 degrees C. 25 degrees C is what we call RT, or room temperature, and 1 atmosphere. You know, 1 atmosphere is, where does 1 atmosphere comes from? 1 atmosphere comes from the average daily pressure, right? Whereas 1 bar comes from the physics, you know, the mechanics, kilogram, meters, whatever else. It's going to come from that. And so let's calculate the molar volume at room temperature in 1 atmosphere. So the molar volume at room temperature in 1 atmosphere is going to equal RT over P. And so R is 0.08206 liters times atmosphere per mole Kelvin. T is going to be 298 Kelvin. 273 plus 25 is 298. And P is just going to be 1 atmosphere. And so atmospheres cancel, Kelvins cancel, that leaves me with liters per mole. And this number I memorized is 24.45 liters per mole. In fact, it's good to forsake phase. We'll just remember it, 24.45 liters per mole. And so in other words, a mole of gas at room temperature and 1 atmosphere pressure occupies about 24.5 liters. 24.5 liters. And so that's pretty convenient for certain things like this. An example of application of that, the molar volume, is, let's look at this reaction. We'll take methane gas plus 2 oxygen gas. This is going to produce CO2 gas plus 2 H2O. And so if I do 1 mole, if I do 1 mole of methane, then I know something. 1 mole of methane at 1 mole of methane at RT in 1 ATM occupies what volume? 1 mole of methane occupies what volume? How many liters? So if I had a mole of methane, it's going to be 24.45 liters. And so take 24.45 liters of methane. That's 1 mole. 1 mole of methane is going to require how many moles of oxygen? 2 moles. So I'll need 2 moles of oxygen. Well, 2 moles of oxygen, how much space will that occupy? 2 moles of oxygen. 48. Yeah, it's going to be 48.90 liters. So if I take 24.45 liters of methane and react it with 48.90 liters of oxygen, then that's a stoichiometric ratio. And if I do that, how many liters of CO2 will I produce? Yeah, 24.45 liters of CO2. And how many liters of water will I produce? 48.90 liters of water. Okay, water is a liquid though. And this is the molar volume of a liquid or molar volume of a gas? This is the molar volume of a gas. So this is not applicable. Do you know what 1 mole of water's volume is? 1 mole of water weighs 18 grams. 18 grams of water has what volume? 18 milliliters. And so actually 2 moles of liquid water is only 36 milliliters, or 0.036 liters. That's it. And so this one doesn't match because it's a liquid. You know, gases are mostly empty space. Liquids are not. Liquids, you compress all the molecules and they're all touching. If this were a gas, if this were steam instead, then this would be correct. And we wouldn't have a problem here. Well, you know, this makes stoichiometry easy because the mole ratio is the same as the volume ratio. And so rather than saying 1 mole requires 2 moles, we could just say for every 1 liter of methane, how many liters of O2 do I need? 2 liters, and I'm going to form 1 liter of CO2. Now the water is more tricky because, you know, it's a liquid. And so this is called Avogadro's law here, Avogadro's. 1 liter, 2 liters, it's the volume ratio. All right, let's do another example here. What is the molar volume of air at 11 degrees C of 1.33 atmospheres? It doesn't matter if the gas is a mixture. Air is a mixture. Right? It doesn't matter because a mole of particles is going to take up a certain amount of space. It's going to weigh different amounts. You know, a mole of these different gases will weigh. For example, methane is going to weigh a different amount than oxygen. Yeah. But what is the molar volume of air at 11 degrees C and 1.33 atmospheres? So molar volume is equal to RT over P. So R 0.08206 liters times atmosphere over mole Kelvin. T, 11 degrees C is going to be 284 Kelvin. P, 1.33 atmospheres. So atmospheres cancel, Kelvin cancel, liters per mole. That's what we get. And so when we look at this, the temperature's colder. If the temperature's colder, will the gas contract or the gas expand? Contract. So the volume's going to be smaller. and the pressure is higher. If the pressure is higher, will the gas expand or contract? It'll contract as well. You know, higher pressures is going to squeeze it into a smaller volume. And so let's go ahead and calculate this. Here is going to be 0.08206 times 284 divided by 1. Divided by 1.33. 2.135. Can't be right. It's too small. I screwed up touching in the calculator. 2.135, it can't compress that much. 0.082, I mean, with these conditions, it can't compress that much. I think divided by 1.33. 17.52. 17.52 liters. It's a little colder, it's going to shrink, and then a little higher pressure, it's going to shrink some more. So it's yeah. Whereas air, you know, a mole of air at 25 degrees C and 1 atmosphere is 25 liters, or 24.5 liters. So it shrunk significantly. 17.5 liters per mole. Okay, let's see. All right, next we're going to do gas stoichiometry. But how often do we work at STP? This is gas stoichiometry at STP. Do we do much? No. So we don't do much at STP. What I'm going to do is I'm going to skip this. Gas stoichiometry at STP. At STP. No, this is not at STP. Here, if you look at it, how many liters of CO2 measured at 744 torr? Well, STP is 1 bar. It's closer to 764. And 131 degrees C will be produced by the complete burning of 16.2 grams of gaseous butane. The equation is given there. All right, so why don't you give this a try here and then see what you can figure out. And then we'll come back.